Welcome, ladies and gentlemen, to your MN40 notes. This is section 10.1 in your textbook, where we're going to talk about the properties of tangents. And as always, when we start a new chapter, I just want to give you kind of a preface of what we are studying, which this chapter is going to be all about circles. So we're going to be talking about relationships with tangents, secants, diameters, chords, inscribed shapes. From there, we talk about arc measure, arc length. We're going to talk about sector area and much more. So this is going to be the chapter on circles. At the beginning of this chapter, we do have a bunch of definitions, as you can see on the note guide: circle, center, radius, chord, diameter, secant, tangent. You're going to use either the glossary in the back of your textbook or section 10.1 in your textbook to define each of these words. It helps a lot for many students to draw a diagram as well and label it so that you can recognize the difference between each of these words. From there, you want to do example number 1, example number 2, and down here the checkpoint. Now all of this on the front of the note guide is very much a review of pre-algebra. Actually, a lot of it is from upper grade school and middle school math, so it's just kind of a good way to remember some of these words that you haven't probably seen in a long time. From there, I'm going to talk you through the points on the back of this note guide. So you want to pause the video right now. You want to complete the front of this note guide. When you're done, you want to, from there, flip the note guide over and resume this video. Thanks. Welcome back. Right away, what we're going to talk about is tangents. And as you defined at the front, a tangent is a line that is outside the circle but brushes up against the circle. And when it does that, it intersects the circle at one spot. And really, you know, we have to use the word intersect very lightly because it's touching the circle, so technically it's an intersection point, but it's not cutting through the circle. At the top there it says tangent theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So this space right here is perpendicular. So when you have a radius, as this is right here, and you have a tangent, if you have those two things and they meet, they're going to meet at the point of tangency, which is right here. This is the point of tangency. And it's going to meet at a 90-degree angle. Now, how does that play, or where does that play into this example number 3? And let's talk about it. Example number 3, it says in the diagram, RS, so we have RS right here, is a radius. So we know that that's the radius of circle R. It's asking, is ST tangent to circle R? So now don't get me wrong, it looks like ST is tangent, but what we don't know for sure is if it is. So let's prove that it is. So what we want to know is this right in here 90 degrees? So is this 90 degrees with a question mark? And as it says down here in the solution, it says uses the converse of Pythagorean theorem. So of course we're questioning whether it's a right triangle. So we use that converse from chapter 7 that we learned at the beginning of the school year, because 10 squared plus 24 squared. So if you look, we have a radius, which is one of the legs, is 10 squared. We have another leg here, which is 24 squared. And we want to know if it's equal to 26 squared. And it is. So because it is, we know triangle RST is a right triangle. And this is kind of fell here. Let me rewrite that up here. And RS is perpendicular to the tangent line, which is TS. Or actually, it's perpendicular. And because it's perpendicular, we know that ST is perpendicular to a radius of circle R at the endpoint of circle R by the tangent theorem. ST is tangent to circle R. So again, if you do actually have a right angle there, or in this case a right triangle, that using the theorem, the tangent theorem, it shows then that RS is perpendicular to ST, which is the radius to the tangent line. So this kind of talks us through a problem, but now let's do an actual problem together and make sure that we're understanding what's happening here. So here's a checkpoint. It says RS, which in this case, if you look, it goes from the center out to the outside of the circle, so that's our radius. So RS is a radius of circle R. Is ST tangent to circle R? So again, what we want to know is, does the radius and this ST line form a 90-degree angle? That's the question, and actually that's really, let me erase that and try it again here. What we want to know is 90 degrees right here. That's the question. Okay. So if that is 90 degrees, then what we have is one leg, RS, which is 12 squared, plus the other leg, which is 16 squared. And we want to know if it's equal to, and now here's the part that you have to be careful with, and I can't stress this enough. Obviously, if we're looking at this as a 90-degree angle right here at angle S, directly opposite is the hypotenuse. So this right here is the hypotenuse, or should be the hypotenuse. Right now, it's showing a length of 7. But just be cautious, because what that 7 is referring to is the point on the circle out to point T. That's 7 right there. Now what you have to decide is from point R, which is the center, out to the outside of the circle, how long that, you need to figure out the length of that. Well, over here we have from the center out to the circle is 12, which is the radius. Well, this green line is also the radius. So this is 12 as well. So any point from the center to the outside of the circle is a radius, and that is going to, in this case, be 12. So we don't have just 12, we don't have just 7, but we have 12 plus 7 as their hypotenuse, which in this case would be 19. So this length right here is 19. So we have 12 squared plus 16 squared equals 19 squared. And we calculate that quickly using our calculator. So 12 squared is going to give you 144. 16 squared is 256. And 19 squared is 361. Well, when you add 144 and 256, you get 400, which is clearly not equal to 361. So this is implying that it's not a right triangle. And actually looking at this, if your a squared plus b squared is greater than c squared, which is in this case, then you're actually talking about an acute triangle, not a right triangle. If it was reversed, it would be an obtuse triangle, kind of taking us a step back again to chapter 7. So what would we say here? Well, here's what I would say. Not a right triangle. So RS, or excuse me, not RS, ST is not tangent. Okay. So determine whether it's a right triangle or not. If it is, you have a tangent line. If it's not, you don't have a tangent line. And simply because the radius and the tangent should meet at the point of tangency at 90 degrees. Now, extending on that idea here, we have example number 4. It says in the diagram, B is the point of tangency. So again, here's that point where the radius and the tangent meet. Well, point of tangency typically is just where the tangent meets, but in this case, the radius and the tangent meet there. It says find the radius r of circle C using the Pythagorean theorem. So they are already telling us that we have a tangent line. So we already know that this right here, using the tangent theorem, is 90 degrees. So we have a right triangle. We need to find the radius, or we want to find the length of r. So we want to use the Pythagorean theorem to set it up. So we have a squared plus b squared equals c squared. The leg, one of the legs, is 77. The other leg is r. And the hypotenuse is the trick, because we have this from point A to the edge of the circle is 49 in length. From the edge of the circle to the center is the radius. So the full length is 49 plus the r. So don't say 49 times r. That's not what we're talking about. We're talking about a chunk that's 49 units long, r units long, and to combine them, it's 49 plus r. So we have 49 plus r quantity squared. Now, we had practiced, or at least this should all of a sudden come to you, that we have a FOIL, or we're multiplying two binomials here, so you want to FOIL this out, just like we did the other day. So we have 77 squared, which in this case is 5,929 plus r squared equals, and again, do not just square each thing inside, you need to expand it out. So here's 49 plus r times 49 plus r. Now I'm going to rewrite this. I'm going to go 5,929 plus r squared equals 49. My first 49 times 49 is 2,401. My outers is 49 times r, which is 49r. My inners is 49r. And my lasts is r squared. And now we can clean this up on the right side a little bit. We have 5,929 plus r squared equals 2,401 plus 49 plus 49 is going to give you 98r plus r squared. So we combine those right there. Okay, so if we're going to start solving for our variables, we want to combine like terms, well actually we don't have any like terms, but we want to start moving things across the equal sign to start getting things organized. The thing that should really jump out at you is this r squared. We have an r squared right here, a positive r squared, we have a positive r squared here. If I subtract r squared from both sides of the equation to combine them, you're going to realize very quickly what happens is they subtract out. So essentially they are gone, which is absolutely lovely, because that makes for a much easier problem. If the r squares don't fall out with subtraction or addition or whatnot, what you end up with is a quadratic, where you're going to use the quadratic formula or factoring to solve it. So let me, on the left side, after we subtract the r squares out, we have 5,929 equals 2,401 plus 98r. From there, I'm going to subtract my 2,401 from both sides of my equation. We have on the left side, let me see, 3,528 equals 98r. Divide out your 98, and you end up with r equals 36. So, and I'm going to say units because I don't know what the measurement is. So we have a radius of 36 units. Okay, so this is really just this whole back side right now has been one main concept, which is essentially that if you have a tangent line and a radius meets it at the point of tangency, it will meet at a 90-degree angle if in fact you have a tangent line. Down here we have just one last idea. It's tangent segments from a common external point are congruent in the diagram below. RS, which is right here, this tangent line, is congruent to this one. Actually, these are segments, but okay, so if for some reason, I mean to kind of keep it simple, but if you have some reason you have over here 2x plus 1, and over here you have 3x, to solve for the x, you would, of course, set them equal to each other, because if you have a point outside the circle and you have tangents hitting that circle at two different spots, those segments are going to equal. So if you subtract 2x from both sides, you have 1 equals 1x. So again, that's subtracting 2x from both sides to solve for x. And so you end up with x equals 1 in this case. Now that's any circle. So if you, a great way to think about this is if you have your planet Earth, you have a satellite out here, that satellite, obviously if you have a tangent line there, tangent line there, this segment here is going to equal that segment here, no matter where that point is outside the circle. Okay, well, so on the front again, that was a review of some terminology that you probably haven't seen in a little while. And on the back, we're talking about that tangent line with the radius and how it intersects at the point of tangency at a 90-degree angle. And then, of course, we have this external point idea. We'll take any questions you have on the work tomorrow. Thank you for tuning in.